I believe the last thing we looked at was how to make a motor and a generator. So, how are magnetic fields actually made?
A changing electrical field produces magnetic field.
Yes. A changing electrical field creates a magnetic field. Or simpler, moving charges generates a magnetic field around them. So, what's the difference between a vector and a scalar?
Vector has a direction.
Yes, vector has a magnitude and direction, while scalar only has a magnitude or value. So, charge, electric charge, vector or scalar?
Vector.
What direction is the charge pointing in? So if I have a point mass, it has a positive charge, and it creates an electrical field around it. The charge is an infinitesimally small point in the middle. So electric charge is a scalar. You could think of it. What about mass? It has no direction. So mass would be a scalar. However, what about gravitational field? So gravitational field pulling everything downward. The gravitational field, or the electrical field, also known as electrical field strength, we often omit the word strength. No. Oh, never mind. These are two different things. Electrical field strength and electrical field. Electrical field strength is like gravitational acceleration. Electrical field is like gravitational. No, I take that back. These are two are identical in electrical force. These two are the same thing. So it'd be like the gravitational force on it. How can you create a uniform electrical field?
What was it? Two parallel.
You take two parallel plates And then if we take a battery, this would be the positive side, that would be the negative side. Then positive, this will become more positive over time. This will become more negative. And we end up creating an electrical field that is uniform. Theoretically, this has to be infinite planes. But we're talking about nanoscale. So as long as you're not near the edges, it makes no difference. So toward the edges, it will start curving outward. So you don't have a nice, neat, uniform field around the edges. But no matter where you are, even if you're close to the surface, in the middle, or close to the bottom source, it's the same. And it's assumed uniform throughout it, even though the edges are slightly done. And do you remember the equation for it? Thought it was electrical field is equal to the distance between these plates, the voltage, and I want to say area. But the original thing assumed infinite, so area makes no sense. Voltage over distance. So if I increase the voltage, you would assume that the electrical field would increase. So voltage needs to be in the numerator. If I increase the distance, you would expect it would decrease. So you need it on the denominator to decrease like that. And there's nothing special about it, so they're linear in voltage and inversely linear in distance. And again, this was based off of infinite area, so area doesn't make any difference. We'll learn what this is later. This is known as a capacitor. Capacitor. It actually stores charge in it. Over time, charge will go to the top, charge will go to the bottom, and you're separating them out, so you're storing charge and energy. If you were to quickly remove the battery, where would all the positive and negative charges go? Well, you remove the wire so they can't flow anywhere. Not exactly true, as they will bleed through the air, and eventually, because nothing likes to stay charged, it will slowly bleed off. Let's say I have a little bar magnet. North, south. Which way does the lines come out? They come out of the north. You can think of north as being positive and south being negative. And where is it strongest at? Yeah, right in here. I forget. Sometimes you can assume it's really strongest inside of it. But especially if you have a solid material, it's very weird. If you have an infinite, like a solenoid that has nothing in the middle of it, it's easier to calculate. But as soon as you put a material in it, it does weird things. I forget honestly what it does, but basically we never could look inside the magnet. But basically, where all these lines are all bunched up, again, you can take the flux. What is a flux, by the way?
The magnetic field times area.
Yeah, it's how much magnetic field is going through a given area. So flux, magnetic flux, is equal to magnetic field times the area. And this is a weird area, as this area has a direction. If you remember, we have the difference between a distance versus displacement. Distance, like for example, if you walk from here to the office and back, you've traveled some distance. Whereas you have zero displacement because it has a direction in it. Which means when you came back, you undid all of your displacement. Area can have a direction too. Basically, if you draw like a surface, and I'm drawing a rectangle, and you go clockwise, then you pick a middle point, and it'll go out like that. Oh, I forget actually the convention, don't rely on it. Whereas if you do the exact same area in the exact same spot but go in the other direction, then it has a different direction. And the direction is going to be always perpendicular to the surface. Even if you had a three-dimensional parabola, then this would have a direction too, depending on how you drew it. I need to turn that down. So I'm creating a solenoid. We can hook it up to a battery. What ways can I increase the magnetic field? What are all the ways to increase the magnetic field of a solenoid?
You have to put more loops in it.
Turn density. Increase the number of turns. So turn density. What else?
What about the length? You have to increase the length,
Mm-hmm.
decrease the length.
Mm-hmm. Anything that would make it weaker.
That's not a lot to do.
Current. How much current is going out of the battery? And the core. What core you used? What type of so let me look up. permeability. Remember, the equation is magnetic field is equal to permeability. No, it's not mu naught, it's just permeability because mu naught is for a vacuum. Then turn density, which is done with a capital N, times current. Usually, I'm going to look up some common values. So this is relative to vacuum. So you just multiply this number times mu naught. So here's an interesting thing. Superconductors have 0. One of the properties of superconductors is they have no magnetic resistance. Let me actually show you a video of it. Superconductor magnetic levitation. So some materials become superconductors when they're cooled to a very, very low temperature. This is one that if you put it on a liquid nitrogen on it and cool it down to the same temperature as liquid nitrogen, it becomes a superconductor. And the thing about superconductors is they have no electrical resistance. Like if you had a long superconductor, you could have almost infinite current going through it and it wouldn't slow it down. Same thing with magnets, magnetism. And basically, as the magnetic field comes from these neodymium magnets through the superconductor, forget the correct explanation. But it basically, maybe I'll explain it.
The first is that they have 0 electrical resistance. But more important for our purposes is the Meissner effect, which causes a superconductor to completely expel magnetic fields when they enter their superconducting.
So they completely expel it. Meaning magnetic fields can't go through it? Oh, because it would have a permeability of 0. 0, I was thinking the opposite. So that means no magnetic fields can go through it, while electrical fields can go through it completely.
State. What that means is that a superconducting material will actually levitate over a magnet, even though the material itself is not magnetic. Now, this is our superconductor, a small disk made of yttrium barium.
Very complicated stuff. Another interesting thing is that's called quantum locking. It's a quantum property of superconductors. So concrete, vacuum is one exactly by definition. Hydrogen, Teflon, copper, bismuth, water, all these are approximately 1. Air, approximately 1, meaning same as a vacuum. Closer you are to 1, closer you are to a vacuum. Stainless steel, this austenitic, I don't know what that means. Interesting enough, a neodymium magnet is about the same as air. So if you were to get a neodymium magnet and wrap wire around it to increase its strength, It wouldn't really do much. I mean, you would be adding the effect of the or the neodymium magnet plus the solenoid, but besides that, it's whenever you get past this. So nickel is about 100 up to 600. Carbon, steel. When you get to iron, and these are all various combinations of iron. Pure iron is 5,000, but you probably won't get a hold to pure iron. And if you do ultra pure iron annealed with hydrogen, get up to 200,000. So wood is only ever so slightly more than air, and air is ever so slightly more than vacuum. It's interesting that copper actually reduces it. So if you were to replace the iron core with a copper core, copper would actually make it worse than air. Which is weird. Wasn't eddy current?
Eddy current?
Mm-hmm. They only mentioned it like a little bit.
I think you said like once or twice.
Yeah. So if I had a large block of iron or copper, it's called copper because iron is magnetic, like can be magnetized, but copper can't, or aluminum. This is from chemistry, but atoms of metal is bonded together by metallic bonding. Basically, the electrons don't stay on the metal too much. So if we can imagine, we have and it's only the outer electrons, their shells, our energy levels. Only the outer energy level electrons, which can only be at most 8, don't stay attached. But you can basically subtract the protons and electrons and just have it so that we have this positive positive inner core, and we have negative electrons that zip around. And because these electrons are forming a C all the way around this, leaving the atoms, what happens is these atoms very strongly, these positive charges will want to repel. These negative charges will want to stay next to the positive charges. But since they're all repelling very strongly, it ends up being all balanced out, and the metal stays very strong together. That's why if you take a hammer, you can bend a paper clip and it won't break. Whereas if you try to bend glass, it instantly snaps. It's extremely brittle. How all the atoms stay together is because the electrons form a C around in the metal. They all constantly flowing around. So you have very loose, easy to move electrons all moving around here. And let's say I drop a magnet onto this. Now, a changing magnetic field creates current. So here's where it's stronger. This little area right here is where it's the strongest. And as it moves down, the strongest region gets closer and closer and closer. So if we can look, I'll draw right on the surface, it's very, very weak. Not very many lines go toward it. But as it gets closer and closer, this point right here is getting an increased magnetic field. And remember, it works both ways. If you have a charge that is moving, it creates a magnetic field. So moving charge creates magnetic field. Changing magnetic field, and you can change the magnetic field in multiple ways. You can change it by moving the magnetic field, causes charges to move. And how they will move, remember what happens when a charge moves in a magnetic field? So if we have a north here, a south here, and we have a charge that is moving in this way, so the magnetic field is going this. Then point my fingers in the direction of the moving particle, my thumb in the direction. This particle will start to be moved downward. So it's going to curve downward, and if this was an infinite source, it'd form a circle. And a circle of electrons, these circles moving, and it depends on their speed. We get multiple little eddy currents. These are called eddy currents. And what happens when we have a moving charge? And it's going to create a magnetic field. So if we're dropping onto this, a north-south magnet, it's going to create a little north-south magnet. Hello? Alright. I'll get it later if it's on y'all's way. Alright, thank you. Bye. And it'll actually prevent it from, it'll repel this magnet up here. That's the reason why if you drop a magnet on something metal, it actually won't slam on it too hard. While these electrons are moving, it actually generates heat as resistance of it. This is known as induction heating. And how powerful do you think induction heating is? Have you ever heard of an induction heater? Oh, come on, look.
Welcome to the future of
Maybe this will give a good explanation.
cooking. Induction is considered the most energy-efficient cooking method available and can be used to prepare any type of food. Let's take a closer look at how it works. It's actually very simple. When a pan is placed on an element, a high-frequency coil below the cooktop surface creates a magnetic field. The heat generated through magnetic friction is transferred directly to the pan, which heats the cookware. Since the area right beneath the pan is the only part of the
So, because there's a force, so it's going down, it's pushing it upward. That means when it's pushing upward, it has to be equal and opposite force, pushing back downward. And the two magnetic fields are pushing on each other, and there has to be some frictions
the element being used. This cooking method wastes less energy than traditional electric or
Ice cube isn't metal. The electrons are very stuck, so they don't do anything.
gas cooktops.
So that means that only the pan is being heated because it's made out of metal, while the ice cube is staying frozen.
Plus, once the pan is removed from the element, the magnetic
That's
connection
not
is
good.
Many of you may not be familiar with control flashes and wireless laptops, microwaves, infrared.
I don't
and
want sales
visible.
advertising. I want physics. Anyway, let me go to the more extreme. That's how a heating thing, so you can put your hand on it, won't do anything, you don't have any metal in your hand. This is some very thick wire. Do you know why it's thick? Because we're going to be pumping crazy amounts of current through it. And it's cold. It doesn't do anything. So, he's creating a magnet field, but a magnetic field doesn't do anything. Remember, it has to be changing. So if you do alternating current instead of direct current doesn't say a thing if you have AC. So that the current is constantly going up and down. That means the magnet field is being created and destroyed, so it's increasing and decreasing. Then, and it's strongest in the center, it's levitating. I think this is lead. A few seconds are running, and starts glowing. So you saw the other one was much faster. So you can generate crazy amounts of heat. And what's happening are those electrons inside of it are trying to spin around in a circle to oppose it. I like this video when he turns it off. In order to do this, it has stupidly dangerous levels of current. And he turned it off, hit the ground, and it solidifies instantly because the concrete below is cold. Oh, here's another good thing. So you can have a magnetic brake. If you have a disc that's spinning, then again, if you track one little point on the disc, then as it goes underneath the magnet, its magnetic field around that point is increasing. And thus it creates these little eddy currents at that point, or tries to. And it's going to resist the magnet and end up slowing down. I wish I had a metal disc that I could rotate and then go put a magnet next to it. One that isn't magnetic, like made out of copper or aluminum. So if I had a solenoid, and the current is going in this direction and out this, where, let me make sure I got the notation right. Dot versus cross into out. I believe. So cross means inward. And a dot means outward. So if I had, for example, a wire that looks like this means it's going into the paper. And if I had a dot, it means it's coming out, so toward the camera. So towards you and away from you. If this side was closer to us, it's kind of hard to draw using these lines. And then this is farther away, farther away. So let me shade the closer side. Which way would the current magnetic field be going? So when I take my thumb and point it in the direction of the current going through this wire, my hand would have to wrap around it so that I would be reaching my fingers into it like that. On this way, my is going down, so my fingers would twist to go in. That's the wrong. I know it's done off this side. This is the correct direction. It is going in that direction. So when the current goes in, I have to rotate my fingers like that. And then but choose the side where it's going into the solenoid, and then when you wrap your fingers, it'll go in.
Excuse me, teachers and students, for a quick interruption. Just a reminder that club organization and screen pictures will be tomorrow. But I need to announce also Bass Club. Your pictures will be tomorrow, so be sure and bring your jerseys those that are in the Bass Club.
So here, yeah, it would be opposite. It's going around it. My hand would go around this way. So it should be pointing that way. See, looking at it on this side. Current goes in. Looks whatever side the current goes into is where the magnetic field goes into or starts.
Can I go give this to Darby and this to Miss Stanley?
Yeah, I suppose. Oh, okay. Reason my thing was this would be in the opposite direction. It would be coming out here, so I'm wrong. Because here, when I wrap my fingers around it, my fingers on the inside will be pointing to the left. My fingers around this loop would be pointing toward the left. Then when I go down, I wrap my fingers in the opposite direction. So it would be going to the left here. So the inside, and remember this portion is the inside. So yeah, that works out. So it would be going to the left. So just think of how you would wrap your fingers and then think about the point in the middle. In the middle side of this, when it's on this side, the arrow's pointing to the left. And on this side, this is the inner side. The arrow's still pointing to the left. So we're looking at left here to be inside coil. And this would also be left here, which is also inside coil. And this right arrow here is outside coil. And this right here is outside coil. Where's it strongest at in a solenoid? The magnetic field? Yeah, it's actually inside of it. And if we just look on the outside, then it would obviously be at the opening. Earlier I said a changing magnetic field causes charges to move. This is slightly missaid. And the bell's about to ring. It's really a changing magnetic flux causes an electromotive force, also known as a voltage, or voltage difference. You can think of voltage as potential energy. Raising a ball up above the ground, when you let go of it, it will move. So as long as the electrons aren't held to an atom, they'll start moving around. We'll continue tomorrow. Make sure we're basically doing a review. I want to move on past this. And you need to do the project. That's it for today.